Okay, so this is the pre-lecture video for tomorrow, kind of late, but better late than never. And we're going to concentrate on the equation for simple harmonic motion. So the mass on a spring is an example of simple harmonic motion. The force of the spring is a restoring force. It's equal to minus kx, where k is the strength of the spring constant. The reason it's called a restoring force is because the force of the spring is always in the opposite direction from the displacement. When the displacement is to stretch the spring tries to bring it back to equilibrium. When the spring is compressed, the spring is trying to bring it back to equilibrium, but again in the opposite direction. So another thing that we can look at is the force of the spring is minus kx. That's also equal to the mass times acceleration. That gives us an idea of where the acceleration is the maximum and the minimum. And wherever x would be the greatest magnitude is where the acceleration will have its greatest magnitude. And that means it's going to be at the end point. So where it's at its maximum displacement, either being stretched or compressed. The acceleration will be 0 when the object is in equilibrium at x equals 0. So when we think about the equation of motion, the equation of motion comes from solving F equals ma. For the spring, it's equal to minus kx is equal to ma, and the acceleration is the second derivative of position with respect to time. So our equation of motion for a simple harmonic oscillator is whatever the solution is to this, what we would view as a differential equation. If we just rearrange it a little bit, we notice that where x is our solution, that's what we're looking for. Its value is something that if we take its time derivative twice, we actually get an answer back that's proportional to x itself. So there's not a lot of choices of the type of function that it could be. It can't be a polynomial. That's not going to work. And it turns out that sines and cosines actually would behave like this, because if we take the derivative of sine and cosine, they just keep going back and forth. And so in math, we might just say that the solution is a linear combination of the two sine and cosine. And I forgot to mention that here, this k over m is often written as omega squared, where omega is the square root of k over m. And so it ends up coming into our answer. So we could write it like this. This is sort of when we learn to solve these types of problems, and this is a very common differential equation that we come across in science. This is the mathematical way that we might solve it. We can use just one of them alone if we introduce a phase angle. And exactly what we do is we choose the solution for the equation of motion. It looks like this. X equals a cosine omega t plus a phase angle. And so we've just chosen to just use the cosine. We could have just chosen to use the sine. The cosine ends up being chosen more often. It's more of the sort of conventional choice to make. I want to look a little bit at what the sine and cosine look like so we can kind of see why it wouldn't make a lot of difference of which one we chose if we just kind of remember the basic facts about the sine and the cosine. The sine takes 2 pi radians to go through one complete oscillation, and the minimum and maximum values that sine has is plus and minus 1. It starts at 0. At pi over 2, which is 90 degrees, it goes to plus 1. At pi, or 180 degrees, it goes through 0. It reaches minus 1 at 3 pi over 2, which is 270, and then finally at 360 degrees, or 2 pi radians, it has gone through one complete oscillation. Now for the cosine, cosine starts at plus 1 at time equals, or t equals 0, And at pi over 2, it's at 0, and it goes to minus 1 at pi, and 3 pi over 2 at 0, and then finally at 2 pi it goes back to 1. And so the sine and cosine are actually very similar. They're just actually 90 degrees out of phase with each other, and so that's why it doesn't really matter. You could just add a phase angle and choose the sine function if you had already had started with the cosine function. So let's take a little bit of time and look and see what the effect of these different constants are in this equation for simple harmonic motion. We're going to look at the amplitude, omega, and the phase angle, and just make sure that we know what all of those do. So first we'll just start with cosine of t, and we know that the cosine of t looks like this. This is 2 pi, and it goes to plus 1 and minus 1. Now the amplitude of the motion for a simple harmonic oscillator is the largest displacement it's ever going to have from x equals 0. So if we put an a in front of the cosine of t, what happens is instead of going between plus and minus 1, it goes between plus and minus a. And so that's what that does. And so just putting the amplitude out in front of there obviously makes it fit our situation a little bit better. Now, if we do a cosine t, now I just want to draw that again, because then we're going to talk about what omega does. And so if I have a cosine of omega t, I know it's going to look like a cosine. Now, normally, what we say is it takes 2 pi radians to go through one complete oscillation, but when we have an omega t here, what's going to happen is omega times t is equal to 2 pi. So t will actually be 2 pi over omega. So this is 2 pi over omega. So what has happened is the oscillation is happening more quickly. So for instance, if omega was 2, this actually would be at t equals pi. It would go through a complete oscillation in half the amount of time that it normally would do. And so what omega does is it really kind of controls how quickly the oscillations happen. And if you go back and you think about the fact that omega is k over m, it should make sense, because we're trying to describe the motion, and omega is, in a sense, how quickly it goes through oscillations. And so it's also, though, dependent on how stiff the spring is and how much mass we've attached to it. And then finally, what does the phase angle do? So again, we'll do a cosine omega t. It just looks like this, and this is 2 pi over omega. But what the phase angle does is, think about, if t equals 0, I still have a phase angle, and so it's possible that instead of the cosine function looking like at t equals 0 being plus or minus 1 or plus or minus a, it's actually, we're not really looking at 0. We're looking at the cosine function where it's phi. And so what the phase angle does is it shifts the cosine function over a little bit, so that at t equals 0, we're not looking at the whole angle being 0, but the whole angle is equal to phi. So it just really just shifts the cosine function to the left by the amount of equal to the phase angle. And so basically the whole idea of thinking about that is when we talk about the description for the simple harmonic motion being equal to a cosine omega t plus phi is we actually want to end up making this equation be very specific for whatever situation we're looking at in that specific time. So the way that we do it is we sort of take our information and also might use what we call initial conditions to figure out what all of these values are so that our equation looks exactly the way it needs to for our particular situation. So, for instance, in this problem, I have a 0.05 kilogram mass on a spring with a spring constant of 1.78 newtons per meter. It's displaced 20 centimeters and then released from rest. So if I pull it aside 20 centimeters and then release it, basically A is 20 centimeters or 0.2 meters. We can find omega as the square root of k over m, which is equal to the square root of 1.78 over 0.05, and that turns out to be 5.97 radians per second. And so I'm almost there. So far, A is equal to 0.2 cosine 5.97 t plus phi. And so then I want to use my initial conditions, which says x is equal to 0.2 at t equals 0. And so hopefully you understand things a little bit better now.